Hello students, welcome back. Finally, are you ready to start the course materials? Here we go. Let's begin section 3, Descriptive Statistics, part 1, Graphical Description. Let's begin with an example. Here's a score distribution of a certain class. I'm not going to reveal which class, which year. The lowest score is 33 and the highest is 94. And as you can see, 6 students scored B in 80s and 10 students in 70s, C, and 4 students in 60s, that's D. And this kind of repetition is called a frequency. So frequency for B is 6. Frequency for A is 1, like that. A relative frequency is the frequency divided by the total. So here in this case, only one student got an A, so frequency is 1, and the relative frequency is 1 out of total 23. How about B? 6 students earn B, so that's frequency, and 6 divided by 23. 6 out of 23 is the relative frequency. And one way to describe this data set using these concepts, frequency and relative frequency, is a pie chart. Here we go. We have 1 student in A, 1 out of 23, 6 students in B, 6 out of 23, 10 students in C, 10 out of 23, etc. Here's the legend. Here, the area of each pie must be proportional to frequency and relative frequency. And how do you do that? Well, the area of each pie is proportional to the center angle, so center angle should be relative frequency, or center angle divided by the total angle of 360 degrees is relative frequency. And if you use radian measure, then center angle divided by 2 pi is the relative frequency. Okay, so much for pie chart. I wasn't going to talk about radian measure. Sorry I mentioned it. Okay, the next example is a bar chart. Similar. We have A, B, C, D, and F, and then height of each box is a frequency or relative frequency. No difference there. 1 student in A, 6 students in B, 10 students in C, and so on. So here we have frequency. Look at this. Goes all the way up to 10. But if you divide each by 23, it's not going to change the shape of this bar chart because it's just a scaling issue. No change in the shape, but the labeling here will change. Instead of 0 to 10, you're going to get some decimals that goes all the way up to 10 out of 23 because it's 0.4 something. That's about it. So whether you use frequency or relative frequency makes no difference in terms of the shape. Okay, so much for the bar chart. Bar charts can be vertical like this or horizontal. It doesn't matter. Personally, I prefer vertical, but you can use horizontal too if you want to. Now, the next concept is Pareto Diagram. By itself, Pareto Diagram is no big deal, and I don't regard it important. But it serves as a stepping stone towards something that is important, ORGIF. I will talk about ORGIFs in a separate video. Here, that's a preparation only. So starting from the bar chart here, Pareto diagram rearranges these bars in an order of most populous, next populous, and then the next populous like this. So bigger frequency to the smaller frequency. So the rectangles go down. And then how about this line graph? This line graph represents the cumulative frequency. Cumulative frequencies or cumulative relative frequencies. So basically here, 10 out of 23, okay, that's where we start. And then the next dot here is 10 out of 23 plus the next relative frequency, 6 out of 23. So I'm adding up is cumulative. And then I add this one up, so I go up again, cumulative. And then accumulate one more, still adding up 2 out of 23, and then add up again 1 out of 23 again. And then I completed adding everything and got to the total, so I stopped at 1, of course. If I use relative frequency here, I have to complete everything at 1. The total over total is 1. And if I use the frequencies here, then I have to end at 23, the total number. Nothing will change the shape of this graph because dividing by 23 of everything is just a scaling issue. So it's not going to change the shape of this diagram. Or the labeling here will change. Instead of going from 0 to 1, we are going to go from 0 to 23, and that's it. Now the Pareto diagram here has two traits. It rearranges rectangles from most populous to least, so it does not work very well with ordinal variables, to tell the truth. For nominal variables, it works well if they are just numbers. But A, B, C, D, F, that's ordinal. Clearly, A is better grade than B, B is better grade than C, and so on. So the rearrangement in most populous to least populous actually distorts that order, so it's not very good in this particular case. But this part, cumulative frequency that's going up, that's an interesting feature, and please remember that when we deal with something that is important or gives. Okay, so much for Pareto diagram. That's just a stepping stone. Now let's go to dot plot, which is a little bit more important than the previous three. So here, each dot represents one person or one number, one datum. So 94, and right here we have a dot at 94. Next, 88, and we have another dot here at 88. Now we have 86 and another 86. We have two students that scored 86. Not coincidentally, we have two dots right at 86. Do you see this? Two dots right at 86. For example, if you go to 77, 4 students scored 77. And then what do you see here? 4 dots at 77. Make sense? So each dot is a score. Each dot corresponds to a datum. By the way, a datum is a singular form of data. And then in the end we have 58, which still has some gap between 58 and 64, but there's nothing like this one. Whoop, and I have 33. This kind of thing is called an outlier. And in many statistical analysis, if you encounter an outlier, an obvious outlier, you just throw it away and then consider the rest. And sometimes you use some mathematical criteria, but that's relatively rare. Most of the time, discarding an outlier is a judgment call. And in case of dot plots, it's very easy to see what is an outlier like this, and also you have a distribution. More population here, more populous around here, and then thin out to the left and to the right. You can see the distribution as well. It's useful. Now let's go to stem and leaf display. Alright, we have a data set sorted out from smallest to largest. We have 33, and this 33 corresponds to 3 and 3 here. So the stem unit is 10 units, and the leaf unit is the next one. So this is 33. Now we have 58. Nothing in 40s, so I don't see any 40s here. Some people have 4 and then blank. I do that, but most people just skip that. So 58 corresponds to this 58. Do you see that? Now we have 64, 67, 67, and another 60. No, 69. Sorry about that. 64779. Now let's go to the stem and leaf display. They're all 60s, and one's digits are 4779. Do you see? 4779, these. Let me highlight these in different color. And then 4779. How about these? 72 to 79. And then do they correspond to these? 70, 2, 3, 3, 5, 7, 7, 7, 9, 9. Yes, they do, of course. Oh, one more. Now, how about these? Let's suppose that you can't see, pretend you don't see any of these, and try to retrieve the data from the stem and leaf display. Can you do it? They're all in 80s, and one digits are 1, 2, 3, 6, 6, 8. 81, 82, 83, 86, 86, 88. Can you do that? That shouldn't be too hard. So you can easily produce a system, you can easily produce a stem and leaf display from the data set when it is sorted out already. Or vice versa. From the stem and leaf display, you can retrieve the data. Also, you can see the distribution. You have a lot of students in 70s, you see. It goes a lot. And then 60s, 80s, a little bit less, and then 90s, it comes down, you see. This kind of thing is called a stem and leaf display. It's important. Among these, I think dot plot and stem and leaf display are the most important. And stem and leaf display is more important than the rest, I have to say. And let me give you a little bit more detail about this part. Stem unit 10, what does that mean? Oh no, never mind. Okay, I don't want the color coding here, so let's go back there. And then let me change this a little bit. Instead of these data, let me change into some decimals like this. So I'm not going to change the non-trivial number part. Instead, I'm just changing the decimal place. So the distribution itself will not change, but everything will become, let's see, a little bit smaller in terms of the position of decimal digits. Bear with me, just one more. Okay, we have a new data set. And then let's go to the stem and leaf plots command in Mathematica. Let's see, stem exponent is 1, so stem is 10th units in this case, and exponent is 1, 10 to the first power. Here, the last digit is leaf part, the stem part is the second decimal digit, 1 over 100, so 10 to the negative second power. Change that to negative second power, and then run this Mathematica program, and let's compare these two stem and leaf displays. What do you see? Exactly the same in terms of distribution, but this one says stem unit is 10, this one says stem unit is 1 over 100, or a second decimal digit. Which data am I talking about? 69, 86, 77, etc. 10th digit, 1st digit. Now let's go to this. 0.069, 0.086, and so on. So the stem unit, that's the second decimal digit, and leaf part is the third decimal digit. So you can change all those decimal digits if you want to. And that's what the stem unit is talking about. If the stem unit is 1000, then I'm talking about 1000 and 3000 and 300, kind of like that. Okay, looks like I went through everything in subsection 3.1, pictorial and tabular methods 1. Now how about pictorial and tabular methods part 2. Well, here we go, histograms and all gives. But they're so important that I'd like to discuss those in separate videos. So we went through a lot of interesting things, and especially dot plot and stem and leaf display are important, but even they pale in the presence of histograms and all gives. So let's talk about these in a separate video. For now, let's stop here. Stay tuned.